Okay, so let's begin. Today's speaker is Dylan Allegretti at the Yao Center at Tsinghua University, and he's going to speak about Teichmüller spaces, quadratic differentials, and cluster coordinates. And the duration of the talk will be about 80 to 90 minutes, I think, but it can vary. So let's welcome him.
Okay, thanks very much. It's good to see all of you here. Thanks for coming. So I'll be speaking about Teichmüller spaces, quadratic differentials, and cluster coordinates. And in the first part of this talk, I'm going to give you a very elementary introduction to Teichmüller theory, beginning with the Teichmüller space. So in this talk, when I say hyperbolic metric, I will mean always a complete finite area Riemannian metric with constant curvature -1. So we will be interested in hyperbolic metrics on surfaces. And so you might ask, how do we get such things? So typically the way it works is as follows. Let's suppose that we are given a compact Riemann surface C, whose genus is bigger than 1. So this surface is equipped with a complex structure, and then by the uniformization theorem, you know that the universal cover of the surface is isomorphic to the upper half plane. And that upper half plane is equipped with the standard Poincaré metric that I've written here, which descends to give you a hyperbolic metric on the surface, on the original surface. So that's typically how we get hyperbolic metrics. And if we have a surface which is equipped with a hyperbolic metric, we'll call that a hyperbolic surface. So that's just the basic terminology that I'll be using. Now, we'd like to consider surfaces with different hyperbolic metrics. And so to do that, we'll suppose that C is a hyperbolic surface, and we'll define a marking of that surface by some auxiliary surface S to be a diffeomorphism between the two surfaces. So this will allow us to have different hyperbolic metrics on a single fixed surface S. And then the pair consisting of the surface and its marking is called a marked hyperbolic surface. We actually would like to impose an equivalence relation on these pairs. So if we have two marked hyperbolic surfaces, C1 psi1 and C2 psi2, we'll say that they're equivalent if there is an isometry of the underlying surfaces that makes this diagram commute up to homotopy. So the composition of these two arrows is homotopic to the other one. That's what it will mean for two marked hyperbolic surfaces to be equivalent. And then we'll define the Teichmüller space in the following way. So let's suppose that we've got a closed oriented surface S. So this is not assumed to have any hyperbolic metric, it's just a smooth surface. And we define the Teichmüller space of that surface to be the space of all marked hyperbolic surfaces up to equivalence. So all pairs, like I was describing before, where the diffeomorphism maps S into some hyperbolic surface. So those are the points of Teichmüller space. And so what is the geometry of this thing? Well, there's a theorem, this is a basic theorem of Teichmüller theory, that if your surface has genus bigger than 1, then the Teichmüller space is homeomorphic to Euclidean space of dimension 6g minus 6, where g here is the genus of the surface. So that's the Teichmüller space, and this is what it looks like geometrically. It's just very simple Euclidean space. And a very natural question, given what I've said so far, is the following. What would be a good representative for a point in Teichmüller space? So you see, I defined the Teichmüller space as the set of pairs And one of the items here is it's a diffeomorphism from S to C. And because these pairs are considered up to equivalence, you don't have just a single marking. You can have different ones representing the same point in Teichmüller space. And what I'm asking here is, can we find one that is somehow preferred? And that question will lead me naturally now to talk about harmonic maps. That's the next topic. So to define the notion of a harmonic map, I'm going to consider here the following setup. So we'll let M and N be two Riemann surfaces, which are equipped with some Riemannian metrics. And I won't consider arbitrary Riemannian metrics. Instead, I'll assume that they have the following type. So I'll assume they're of the following type. So for any local coordinate Z on the surface M, and any local coordinate W on N, we'll assume that the metric tensors are given in terms of these local coordinates by these expressions, where G and H are some positive functions on the surfaces. So these local coordinates are complex valued local coordinates on these Riemann surfaces, and these are giving you local expressions for the metrics on those surfaces. And so we'll assume that this sort of expression exists for any local coordinates on the surfaces. And such metrics are sometimes called conformal metrics because they are conformally equivalent to the uniformizing metrics on those surfaces. And then we'll suppose that we've got a map, F. So F is a smooth map from M to N, and we'll assume that it takes the domain of the local coordinate Z to the domain of the local coordinate W. So here I've illustrated a picture of my setup. I've got the two surfaces. Each of them has some specified local coordinate, and then F is the map between the surfaces that relates the domains of these local coordinates. It sends this one patch to the other. Okay, so that's the basic setup. Now, how do we define this notion of a harmonic map? First, I will define this invariant, which is called the energy density of F. And it is a function on the surface M, which is given by this expression here. So you can see that it involves the metrics on the two surfaces, which are described by these functions G and H, and it involves the derivatives of this map F. So that's the energy density. We also consider, and I should say that this is defined in terms of a local coordinate Z, but then one has to check that that these expressions patch together to give a well-defined global function. So that is the energy density. And then you can define the total energy by taking the integral of that energy density over the entire surface. And here we integrate with respect to this volume form associated to the metric G. So that's defining the energy, which you can think of as a functional on the set of all smooth maps between these Riemann surfaces M and N. So to every smooth map, we associate this energy, and then a harmonic map is defined to be a critical point of this energy functional. So that's intuitively how you should think about it. It's a harmonic map is a map that in some rough sense minimizes the total energy. Of course, as usual, when we do these, when we're talking about the calculus of variations, we replace this condition that F is a critical point. We replace that by some differential equation. So there's an equivalent way of saying this. Let me tell you what that is. So a map F is harmonic if and only if it satisfies this partial differential equation. So this would be the Euler-Lagrange equation for the variational problem that I described on the previous slide. So a map is a critical point of the energy if and only if it satisfies this equation. And basically, we're not going to use this equation, but the one thing that you should note about it is that it explicitly involves the metric on n. So you can see that this function h appears here in the equation, but the equation does not depend on the metric that we put on m. So there was this other metric g that doesn't appear in the equation. Rather, this condition depends on the conformal structure of m. So you can see that there's this local coordinate z appearing here. That's a sign that this equation depends on the conformal structure of m. So later on, when I talk about harmonic maps between Riemann surfaces, I will often tell you, well, I'll have to tell you what the metric is on the target surface, but I may not specify a metric on the domain surface. It's enough to just tell you that it's a Riemann surface, and then you can make sense of this notion of a harmonic map. And right. Okay, so that is the notion of a harmonic map. Now, I'd like to discuss a little bit more generally what one can do with a smooth map between Riemann surfaces. So let's say that F is any smooth map. It doesn't have to be harmonic. Given such a map, you can take the metric on the target surface. So that had this form H dw dw bar. You can take that metric and you can look at its pullback via the map F. So when you pull back, you will get some tensor on the domain surface M. And that tensor will have several terms in it, one of which has this form, phi of z dz squared. So in other words, I'm looking at the 2-0 part of the pullback. I'm looking at all terms that are multiples of dz squared. And you can actually compute explicitly what this function phi of z is. It's kind of an elementary calculation to show that phi of z is given by this formula. So it involves the derivatives of f and also the metric on the target. And this expression will be very important actually. So first let me tell you something about it. If your map is harmonic, if f is harmonic, then this function you can show is holomorphic. And so you could think of this expression here, this phi of z dz squared in that case, as what's called a holomorphic quadratic differential. That just means something that's a holomorphic function, or locally it's a holomorphic function times dz squared. And this has a name. So this expression is called the Hopf differential of f. So for any smooth map, we can take the Hopf differential, which is a quadratic differential. And if the map is harmonic, then that Hopf differential will be a holomorphic quadratic differential. So that's something you can do with a harmonic map. And I'd like to give you now an example. So for this example, I'm gonna keep it very simple and take my Riemann surfaces to be just the complex numbers and the upper half plane. So m is the complex numbers, n is the upper half plane, and each of those is equipped with a standard metric. So on the complex numbers, it would just be the usual Euclidean metric, and on the upper half plane, it's the Poincaré metric that I wrote down earlier. So you have those two Riemann surfaces with Riemannian metrics, and then we can do the following. So starting in the complex plane, I'll take a complex number z, and I'll map it to its real part. So that provides a map from the complex plane to the real line. And then what I'll do is embed the real line isometrically as a geodesic in the upper half plane. And if you've ever studied hyperbolic geometry, then you know a geodesic in the upper half plane looks like this. It looks like a Euclidean half circle that meets this real line at a 90-degree angle. So then you can take the composition of these two maps. That gives you a map from complex plane into the upper half plane. And that composition is a harmonic map. So later we'll be interested in harmonic maps that are diffeomorphisms. This, of course, is not a diffeomorphism because it maps the whole plane to just this one-dimensional geodesic arc. But nonetheless, this is an example of a harmonic map. And if you take its Hopf differential, you find that it's just a constant multiple of dz squared. So using that formula that I had on the previous slide, you can compute that the Hopf differential of this map is 1/4 dz squared. So that's a basic example. There's a very explicit example. In general, we are not able to be so explicit when writing down, or we can't explicitly write down formulas for harmonic maps. Instead, we're going to have to use some existence and uniqueness results to get examples of these things.
The second map is isometric embedding?
Yes, isometric embedding. That's right.
Yeah.
So how do we get examples of harmonic maps? So there's a theorem here that that's based on the work of a number of different people here. So let's suppose that M and N are compact Riemann surfaces, and also that the metric on N has negative curvature. So you could take, for example, the uniformizing metric on a compact Riemann surface N. And if the genus is at least 2, then that's a hyperbolic metric, so it has negative curvature. And then if F is a diffeomorphism between those surfaces M and N, then the statement is that F is homotopic to a unique harmonic diffeomorphism. So you start with any diffeomorphism, and by modifying it a little bit by a homotopy, you can get a harmonic one. That's the theorem. Now, we're going to apply the theorem in the following way. So as before, let me assume that S is some compact Riemann surface. And we'll use the theorem now to construct a map from the Teichmüller space of S to this space, this vector space of holomorphic quadratic differentials. So here I write Ks for the canonical bundle of S, or the holomorphic cotangent bundle. And so this vector space is the space of all holomorphic quadratic differentials on S. And the way this map will be constructed is as follows. We'll take a point in the Teichmüller space, which, as I've said, is a pair consisting of a hyperbolic surface and a marking. And by the theorem, we know that that marking is homotopic to a unique harmonic diffeomorphism. So we'll take that harmonic map and we'll take its Hopf differential. And by the lemma I had previously, the Hopf differential is a holomorphic quadratic differential. So we end up with a point here in this space. And that is how you define the map. You're sending a point to the Hopf differential of the unique harmonic diffeomorphism homotopic to the marking. So you get this map, and then it's a theorem that was proved independently by Hitchin and Wolf that this map phi is actually a homeomorphism. So another way to think about it is you're giving a parametrization of Teichmüller space by holomorphic quadratic differentials. So if you have any Riemann surface, then its Teichmüller space is in bijection with the space of holomorphic quadratic differentials on that Riemann surface. So this is the basic result that we would like to generalize here. And how are we going to generalize it? Well, that's the next thing. So I'm going to begin with a question. The question is, what happens now if we allow our Hopf differentials to have poles? So up until this point, we were talking about holomorphic differentials on compact Riemann surfaces. So they were globally holomorphic. But the question now is, what happens if we let these differentials blow up at some discrete set of points? What if they can have poles? So to answer this question, I'll have to introduce a bit of notation. Let me first fix a compact Riemann surface S, and then let me write P for a finite set of points on that surface. And you can think of these points as the poles of meromorphic differentials on S. So these will be the poles of our Hopf differentials. And then we'll consider meromorphic differentials like this. So here I introduce this divisor D, which is the sum over all points in P, where each one has coefficient 2. So in other words, I'm considering here meromorphic quadratic differentials with poles of order at most 2. And everything that I'm about to say actually could be generalized. So you can actually formulate versions of all of my results where you allow the poles to have arbitrary orders. But here, just for simplicity, I assume that the pole has order at most 2. Okay, then near any pole P, we can write our differential in terms of a local coordinate Z in this way. So we have a local coordinate that vanishes at this point P, and we can write the differential as some Laurent series times dz squared, where the most singular term of the Laurent series has this form. It's AP times z to the minus 2. So that number AP is called the leading coefficient of the differential at P, and it turns out to be independent of the choice of local coordinate. So if I chose a different local coordinate, I could again write the Laurent expansion near this pole P, and the leading coefficient would be the same number. Okay, that's what the leading coefficient is. And now, supposing I choose any vector of complex numbers. So I choose a bunch of complex numbers A sub P, then I can write this expression QA of SP to mean the space of differentials, quadratic differentials, whose leading coefficient at P is this number AP. So I'm defining now a space of quadratic differentials that have prescribed leading coefficients. And those leading coefficients are given by this vector A. So that's one space that we have. On the other hand, we can consider hyperbolic surfaces that have now punctures and totally geodesic boundary components. So an example of such a thing would be this. So this is meant to be a hyperbolic surface. It has genus 1, and it has 3 boundary components, illustrated here. And it has 1 puncture. And because we consider hyperbolic metrics that are complete and finite area, it follows that in a neighborhood of the puncture, the geometry looks like this. It looks like a cusp. So you have this infinitely long thing as you approach the puncture. So we'll consider hyperbolic surfaces like that. And just as before, we can define a marking of such a thing. So a marking of a hyperbolic surface by this pair SP is defined now to be a diffeomorphism from this punctured surface into the hyperbolic surface that you get by deleting the boundary of C. So that's a marking. And then just as before, we can define an equivalence relation. So actually first, these pairs are just like I did before, that we're going to call them a marked hyperbolic surface. And we say that two marked hyperbolic surfaces are equivalent if there is an isometry of the underlying surfaces that makes a certain diagram commute up to homotopy. So these two maps are homotopic. That's what it means for these marked hyperbolic surfaces to be equivalent. Okay, so all that is very similar to what we had before. It's just that now we are allowing our surfaces to have punctures and totally geodesic boundary components. Okay, and now for any vector of positive or non-negative real numbers, we can write T sub L to mean the space of equivalence classes of marked hyperbolic surfaces, such that if this coordinate LP is a positive number, that means that P corresponds to a boundary component of the surface with length LP. And if LP is 0, then P corresponds to a cusp in the surface. So this vector L is giving us a bunch of non-negative numbers which prescribe the lengths of the boundary components of the surface. And like we did in the case of quadratic differentials, we can consider the space of things with these prescribed boundary data. So that's this Teichmüller space that I'm denoting T sub L. Okay, and then there's a theorem here, which says if your punctured surface has negative Euler characteristic, then it is homeomorphic to Euclidean space of dimension 6G minus 6 plus 2D, where G is the genus of the surface and D is the number of marked points. All right, so and here I'm talking about the Teichmüller space where I fix the boundary lengths. So that is the space of having this dimension. And here's a theorem that I proved in my most recent paper. So let's say that we have a vector A. This is a vector of complex numbers. And let's define a corresponding vector of non-negative real numbers by this formula. So it's a little bit complicated, but don't worry about the details of this. We're just defining some positive real number in terms of the absolute values of these numbers A and their arguments. So here theta P is denoting the argument of A sub P. Okay, so given any vector of complex numbers, we define this corresponding vector of non-negative real numbers. And then there is a canonical homeomorphism between this version of Teichmüller space where I fix the boundary lengths and this space of quadratic differentials where I fix the leading coefficients at every pole of the differential. And this homeomorphism is just a direct generalization of what I was talking about before, this result of Hitchin and Wolff, and it's defined in the same way. So if you take a point in the Teichmüller space, you're taking a harmonic map homotopic to the marking, and you're mapping it to the Hopf differential. That's how you get this homeomorphism. So I should say that this result extends, it builds on the work of a number of people. In particular, these authors, Wolf and Lohkamp, studied Hopf differentials with poles back in the early 90s. And then also some similar work was done more from the perspective of the theory of Higgs bundles by Carlos Simpson. And there are other people who have worked on similar things. So I'm sorry, I'm leaving out some names here. So this is a generalization of previous work. And I should also mention that it can be extended. So you can allow higher order poles. And in that case, you'd be generalizing a theorem of Shivajoy-Gupta. So he considered the case where you have a surface and your Hopf differential has poles of order at least 3. So if you look in my paper, then you can find the most general version of this theorem where you can have poles of any order. And here I've explained the case where the poles have order at most 2. Okay, so that's one way you could generalize this classical result of Hitchin and Wolf. But actually we can look for some further generalization. So the next question is, what happens if we allow the complex structure of our Riemann surfaces to vary? So in these results up until now, I was fixing a complex structure on my surface and then parametrizing the Teichmüller space by holomorphic quadratic differentials for that complex structure. But what I'd like to do now is consider somehow all possible complex structures on a fixed smooth surface. So to do this, I'll introduce first a bit of notation. I'll let this bold S denote a closed oriented surface. And I'll denote this kind of bold P, I'll let this bold P denote some finite set of points on the surface. So here, I do not fix any kind of complex structure. These S's are smooth surfaces. That's why I use the different notation. I use this bold S to denote a smooth surface as opposed to a Riemann surface with a complex structure. And so here's a bit of terminology. So by an automorphism, we will mean an orientation preserving diffeomorphism of the surface that induces a bijection on the set of marked points. So an automorphism is allowed to permute the marked points. It doesn't have to fix them. 2 automorphisms will be called isotopic if they are homotopic through automorphisms. So you have a homotopy, which at every time t defines an automorphism of these surfaces. And then finally, we'll define the mapping class group to be the group of automorphisms of one of these punctured surfaces up to isotopy. So we take isotopy classes of automorphisms and equip that set with the natural composition. So that's just basically the usual, I mean, it's the classical definition of the mapping class group of the surface. Maybe the only thing worth pointing out here is that we allow our automorphisms to permute the marked points. Okay, so that's the mapping class group. And what we'll do is this, we'll consider triples of data where S, as before, is a compact Riemann surface, and phi is a meromorphic quadratic differential with poles of order at most 2. So the poles occur at points in this set P. And then finally, we have this map theta, which is a diffeomorphism from the smooth surface to the Riemann surface. And this diffeomorphism should induce a bijection from the set of marked points to the set of poles of the differential. So if we specify such a triple of data, we're basically saying we're specifying a meromorphic quadratic differential, and then we're saying how to put it back on this smooth surface bold S. So this is like this theta is like a marking of that surface. So we'll consider triples like that. You can show then that there is a nice moduli space parametrizing equivalence classes of such triples. And if the punctured surface has negative Euler characteristic, then this moduli space, in fact, has the structure of a complex manifold of dimension n, where n equals 6g minus 6 plus 3d. Here, g is the genus of the surface, and d is the number of marked points. Okay, so we have a complex manifold parametrizing quadratic differentials on varying Riemann surfaces. So part of the data of a point in this space is a Riemann surface, which is diffeomorphic to our fixed smooth surface. On the other hand, on the Teichmüller theory side, we can consider pairs where C is a hyperbolic surface. And again, we do punctured hyperbolic surfaces, or surfaces with punctures and boundary. And here, psi is a marking of that surface by this pair SP. So this is defined in the same way as before, but now there's no assumption that this surface has any complex structure. It's just a smooth surface. So one also has a moduli space parametrizing equivalence classes of such pairs. So you have kind of Teichmüller space defined just as before. And if your punctured surface has negative Euler characteristic, then this space has the natural structure of an orbifold of real dimension n. And n here is exactly the same n I had before. So before we had a complex manifold of dimension n, now we have a real space of dimension n. So this has half the dimension of what we talked about before. And I'll explain a little bit later why you should think of this as an orbifold. So we'll come back to that. First, let me just say the mapping class group, it acts naturally on both the space of quadratic differentials and on this version of Teichmüller space, right? So if you have a mapping class, you can just pull back a quadratic differential or a hyperbolic structure that gives an action on these two spaces. And one of the theorems I proved is this. Again, if the surface has negative Euler characteristic, then there is a continuous mapping class group equivariant map from the space of quadratic differentials to the Teichmüller space. And it's defined in basically the same way as this as these other maps. So before we had a homeomorphism between two spaces, right? We had the Teichmüller space and a space of quadratic differentials, and they were homeomorphic. So basically what I'm doing here is taking a quadratic differential and I'm sending it to what you would get by applying that homeomorphism from before. The difference now is that I consider all possible complex structures on my surfaces here. So this space has twice the dimension of this one. So I'm no longer getting a homeomorphism of spaces. This is rather just a continuous mapping class group equivariant map. And so let me get back to this question now. How can we understand the orbifold structure of this space, of this Teichmüller space, T of SP? So I told you it was an orbifold, but I didn't explain how it is an orbifold. Like what are the points of this space that have non-trivial automorphisms? So now I'd like to explain that. And this will lead me to the definition of what's called the enhanced Teichmüller space. So before I get there, let me say something about quadratic differentials. So let's let phi be a quadratic differential on Riemann surface S, and suppose that its leading coefficient at P is some number AP. Okay, so remember that's the leading coefficient in the Laurent expansion at P. Then I can form this expression plus or minus 4 pi I times the square root of AP. That expression is called the residue. And because I'm taking the square root here of a complex number, this expression is well defined only up to a sign. So it's plus or minus this expression here. And we can get a finite cover of our space of quadratic differentials by choosing a value for this square root. So to say it a different way, this cover here is parametrizing points in the space of differentials together with a choice of sign for the residue at every pole of order 2. So at a pole of order 2, I have this expression here, which is only defined up to a sign. And to get a point in this covering space, what I'm doing is choosing a definite value of that expression. So I choose an actual number rather than just plus or minus a number. So that will give me a cover. It's a branched finite cover of the moduli space of quadratic differentials. And we can do a similar thing also on the Teichmüller side. So there's something called the enhanced Teichmüller space of a surface. And this is a similar finite cover. It parametrizes points in the Teichmüller space together with a choice of orientation for each boundary component of the hyperbolic surface. So a point in this space would look like this. It's a hyperbolic surface, and anytime you have a boundary component like here, you have to choose an orientation. So choose a little arrow going in one direction or the other around that boundary component. So that data defines a point in the enhanced Teichmüller space. And I have a theorem here that if your surface has negative Euler characteristic, then there's a continuous mapping class group equivariant map from this this space of quadratic differentials with this sign, with this choice of sign, to the enhanced Teichmüller space. And here I should explain, I have written MCG plus minus to mean this extension of the mapping class group. So I take the semi-direct product with this finite group Z mod 2 to the P. That group acts in the obvious way on these two spaces. So the second factor, it acts on the space of signed differentials by just changing the choices of sign at each of the points of P. And it acts on the enhanced Teichmüller space by reversing the orientations of boundary components. So if you form this extended mapping class group, then the map I'm talking about here is equivariant with respect to the action of that group. Okay, so this map is a lift of what I described earlier. I talked about a map from moduli space of quadratic differentials to Teichmüller space. now I'm lifting to these finite covers. Okay, so how does this help us understand the orbifold structure of the Teichmüller space? Well, what I'd like to claim now is that this enhanced Teichmüller space is actually a real manifold. So this finite group Z mod 2 to the P acts on enhanced Teichmüller space, and the thing I had before is the quotient by that group action. So if I can show that this enhanced Teichmüller space is a real manifold, it will follow that the space I talked about before is a real orbifold. And to explain this, I'm now going to talk a bit about cluster coordinates on the enhanced Teichmüller space. So to define these coordinates, I'm going to have to choose a bit of extra data. So we define an ideal triangulation of one of these punctured surfaces to be a triangulation of the surface whose vertices are precisely the points of P. So you take your surface with its marked points, you draw arcs connecting the marked points, and as soon as you've got enough arcs to make a triangulation, that's called an ideal triangulation. And so if C psi is a marked hyperbolic surface in this enhanced Teichmüller space, then we can use the marking to draw each edge of the triangulation as a curve on the hyperbolic surface. So remember that a marking is a map from the smooth surface S to the hyperbolic surface C. And so if we have a triangulation of S, we can draw its arcs on the hyperbolic surface. And if we do that, then we get this picture on the right-hand side. So this is a picture of an arc. So we've taken an edge of the triangulation, an edge alpha. We've mapped it onto the surface C, and that gives us some arc that maybe ends at a boundary component, or maybe at a cusp of C. And if you lift that picture to the universal cover, you would get something like this. So this geodesic here maps down to the boundary geodesic on the surface. And then this wiggly line is a lift of this arc. Okay, so we can do that. And then what I'd like to do is the following. We can straighten this arc to be a geodesic on C that spirals into the boundary components in the direction given by the chosen orientations. So remember that a point in enhanced Teichmüller space also has these chosen orientations as part of its data. And what I'm saying is you can take that arc that before was just ending on a boundary component, and I can let it spiral into the boundary component in this direction given by the orientation. So that's a sort of a vague way of saying it. A more precise way is to say what happens in the universal cover. So before we had a wiggly line that was ending on this geodesic in the upper half plane. And what I'm saying is take the endpoint of that geodesic and endpoint of that curve and drag it along this geodesic until you get to infinity, and then straighten so that you have this geodesic arc ending at the boundary at infinity. So that's a way that you can draw all of the arcs of an ideal triangulation as geodesics on this surface C. We can do this for any arc of the triangulation. So let's let alpha now be an arc of T, and let alpha tilde be a corresponding geodesic in the upper half plane that we obtain by this procedure. So it's one of these geodesics that spirals into the boundary. And if we do this for all arcs, then they determine an ideal quadrilateral in the hyperbolic plane. Here I'm viewing the hyperbolic plane in the Poincaré disk model. So we get an ideal quadrilateral whose diagonal is this geodesic alpha tilde. So alpha tilde is one of these geodesic lifts, and the nearby triangles give you other geodesics forming an ideal quadrilateral. So I will label the vertices of this quadrilateral as Z1, Z2, Z3, Z4. And then the natural thing to do whenever you have 4 distinct points in CP1 is to take their cross ratio. So we can do that. We can define X sub alpha to be the cross ratio of the 4 points defined by this formula. And that number is in fact independent of all the choices that we made in the construction. So it's independent of the choice of lift to a geodesic in the hyperbolic space. It's independent of the choice of labeling of these vertices, things like that. So you can check that this number depends only on an arc of the ideal triangulation and a point in enhanced Teichmüller space. So that's how you get some numbers corresponding to a point in enhanced Teichmüller space and a choice of triangulation. And it is a fact that for any ideal triangulation, these numbers provide a homeomorphism from the enhanced Teichmüller space to this real manifold. So this is a product of n copies of the positive real numbers, where n is the number of arcs of my ideal triangulation. So that gives a proof, if you believe me that this is a homeomorphism, that shows that this enhanced Teichmüller space has the structure of a smooth manifold, as I was claiming before. And these X alphas are quite important. So they go by various names. Sometimes they're called cluster coordinates or Fock-Goncharov coordinates. And they're also the exponentials of Thurston's shear coordinates. So in some form, they go back probably to the 1980s and were studied by Thurston and his collaborators. So they're quite old. And another interesting thing about them is they transform by some special rational transformations, by the so-called cluster Poisson transformations, whenever we change the ideal triangulation. So I won't go into that, but that's how this whole subject gets related to cluster algebras, cluster varieties. It's because you have these special coordinates on the Teichmüller space that transform by these interesting formulas. Okay, so at this point we've discussed the enhanced Teichmüller space. We've got some special coordinates on that space. And what I'd like to do next is tell you about some other coordinates on the space of quadratic differentials. So suppose now that we're given a point in that space. So remember that a point in this moduli space consists of a Riemann surface and a quadratic differential on that surface, and then a marking, which is it's a diffeomorphism from this smooth surface bold S to the Riemann surface S. So given such a thing, we can write S circle to mean the punctured surface that we get by deleting all the double poles of the quadratic differential. So get rid of those points. You're left with a surface S circle. And we can define the spectral cover to be the branched double cover of this punctured Riemann surface defined by this formula. So let me explain what's going on here. As before, K sub S is denoting the holomorphic cotangent bundle. So we can think of this sigma as living inside the total space of the holomorphic cotangent bundle. And locally, in a trivialization of that bundle, we can think of a point as a pair where you've got a point Z on the Riemann surface S and a holomorphic cotangent vector lambda. So the requirement here to be a point in sigma is that lambda squared gives me the value of my quadratic differential at Z. Right? So phi is some tensor on this Riemann surface. And its value at Z should be equal to the tensor square of this holomorphic cotangent vector lambda. So that defines some subspace of K sub S. Because there are generically two square roots of any complex number, you can see that it's a branched double cover of this Riemann surface, and that's called the spectral cover. We'll also write tau for the involution exchanging the two sheets of this cover. So tau is the non-trivial deck transformation that takes a point on one sheet and maps it to the corresponding point on the other sheet. Or in other words, it takes a square root of phi of Z and maps it to the other square root. Okay, so that's some notation that we'll be using. I will also introduce this set gamma, which is the collection of vectors in the first homology of the spectral cover, which are anti-invariant under the covering involution. So if you like, this is the -1 eigenspace of tau acting on the first homology of sigma. And that, in fact, has the structure of a finitely generated free abelian group. So it's a lattice. And by definition, you can see that this square root of the quadratic differential is well defined on this spectral cover, right? Because the spectral cover is parametrizing choices of square root of phi at any given point. So there's a tautological one form on that surface, which you can think of as a square root of phi. And so what we can do then is we can define a group homomorphism from this lattice gamma to the complex numbers by taking periods. So if we have any vector in the lattice, we just integrate this one form around that vector. That will give you some complex number, and it defines this period homomorphism that I denote Z sub phi. So we would like to use this now to define some kind of coordinates on the space of quadratic differentials. So what we do is this. If you have any point of a Riemann surface which is not a zero or a pole of the differential, you can show that there is a local coordinate W in a neighborhood, defined in a neighborhood of that point, and unique up to multiplication by -1 or addition of a constant, such that the differential is expressible in terms of that local coordinate as dw squared. Okay, so near any point of S, as long as it's not a 0 or a pole, you can find a local coordinate W such that the differential takes the form dW squared. And then you can talk about these lines where the imaginary part of that local coordinate remains constant. So that equation makes sense because the imaginary part doesn't care if you multiply by -1 or if you add a constant. It will be this equation will remain true even if you modify W by such a transformation. So this condition defines a singular foliation of the surface. And just to give you an example, it could look something like this. So here I've illustrated some leaves of a foliation. It's singular because you can see there are some points here denoted by these little X's where 3 leaves come together. So those points are simple zeros of the quadratic differential. So this foliation will be singular at the zeros and poles of the differential. And typically, a typical picture looks like this. And what you can do then with this picture is, if the differential is sufficiently generic, it will determine a decomposition of the Riemann surface into strips. So you get these horizontal strips of the form of this form. It's complex numbers whose imaginary part lies between 2 values. So maybe it's not clear what that looks like on the surface. So let me show you. It looks like this. So this shaded region is being mapped by the local coordinate to something like this, to a strip in the complex plane. And the foliation is giving you a decomposition of the Riemann surface into things like that. So the whole surface is composed of these strips glued together along their boundaries. Okay, so that's what you can do given a sufficiently generic quadratic differential. And then in each strip, we can draw a curve connecting 2 zeros of the differential, whose image under the distinguished local coordinate is a straight line. So an example would be this blue curve that I've drawn here. So the shaded region, again, is this horizontal strip. And then you can draw a curve going through that strip that connects these zeros on the 2 sides. And the image of this segment under that distinguished local coordinate W would just be a straight line in the complex plane. So such a curve is called a standard saddle connection. And we're interested in the corresponding picture on this double cover, on this spectral cover. So you can lift that blue curve to the spectral cover. And notice that these X's, these endpoints of the curve, are branch points for the spectral cover. So if you do that, you actually get a closed loop upstairs. So you get a loop up in the spectral cover, and actually there's a way of canonically choosing an orientation for that loop so that it defines a class in the first homology of the spectral cover. And if we do this for a standard saddle connection, the class that we get will be called a standard saddle class. Okay. So given the differential, we've defined these special cycles in homology. And finally, what we'll do is the following. So if we have a generic differential, it is a fact that these standard saddle classes form a basis for the lattice. And we can take their image under this period homomorphism, so we can integrate the distinguished one, the canonical one form over each of these standard saddle classes, and we'll get some numbers. Those numbers are called the period coordinates of the differential. So I realize this construction was a little bit complicated, but the point is that I've associated to any generic quadratic differential some complex numbers. And the question now is, how are these period coordinates, how are the period coordinates of a differential phi related to the cluster coordinates of the corresponding point in enhanced Teichmüller space? So remember, we have a map from this space of quadratic differentials to the enhanced Teichmüller space, and we have some kind of numbers that we can associate both to the quadratic differential and to the point of Teichmüller space that we get by applying this map. And the question is, what is the connection between those coordinates? So that is what I would like to talk about next. And to do this, I will have to introduce something called the WKB triangulation. So the way this works is, again, we'll fix a generic point in the space of quadratic differentials. And as I explained, that point determines a foliation of the Riemann surface and a decomposition of that surface into these strips. So what we could do then is choose a generic leaf of the foliation within each strip. So here I've got my foliation, and in blue I've illustrated a leaf chosen from each of the strips in the decomposition. And if you look at this, you can kind of see that it looks like a triangulation, right? So around each of these trivalent points, you have these three blue arcs. And indeed, if you take the preimages of these leaves under this diffeomorphism theta, remember theta is the marking, it is a map from the smooth surface to the Riemann surface. If you take the preimages of these leaves under that map, they will indeed form an ideal triangulation of this surface. And that triangulation is called the WKB triangulation. So we talked earlier about how to assign cluster coordinates to an ideal triangulation. And here I'm saying if you have a quadratic differential, a generic quadratic differential, then there is a canonical choice of ideal triangulation of the surface. So we could take, for example, the cluster coordinates with respect to that triangulation. Okay, now you can see from the construction that there is a natural bijection between the standard saddle classes. These were the classes in homology that we associated to these standard saddle connections, and edges of the WKB triangulation. Why is there a bijection? It's because both of these things were associated to horizontal strips that decompose the surface. So they're in bijection with each other. And I will write gamma sub j for the standard saddle class corresponding to an edge j of the WKB triangulation. I will also, for any real number r, I will write this notation, x phi j of r, for the cluster coordinate of this point of enhanced Teichmüller space with respect to the edge j. So what I'm doing here is taking a quadratic differential, I'm rescaling that differential by multiplying by r squared, and then I'm taking its cluster coordinate. And to take the cluster coordinate, I have to specify an ideal triangulation. The one I'm taking here is this WKB triangulation, which is determined by the differential. Okay, so these x's are just some cluster coordinates. And And there's a theorem here. You can ask, how do these coordinates behave? And it turns out that their asymptotic behavior as r goes to infinity is controlled in some sense by these period coordinates. So they can grow or decay exponentially. They go like exponential of minus r to the real part of z. And z here is the period coordinate associated to this edge j of the triangulation. So there is a relationship between the period coordinates and the cluster coordinates, but it's a rather subtle one. It's not like they're just equal or something. They can't be equal. Instead, it's an asymptotic relationship that you have. As you go off to infinity in the space of quadratic differentials, the period coordinates control how the corresponding cluster coordinates are growing on the enhanced Teichmüller space. All right, so that was the final result that I wanted to present to you. And in the remaining time, I'd like to talk about some of the implications of this work and some conjectures that I have. So just to summarize, we've described here a natural map going from this space of quadratic differentials with these chosen signs at every pole of order 2, going from that space to this enhanced Teichmüller space. And there are many open questions about this map. So, for example, I told you that this map is continuous, but maybe you would want to have some stronger regularity properties for this map. For example, here I conjecture that this map is actually real analytic. And I tried to prove this, but it seems to be a little bit tricky. I believe that one can show this using the analytic implicit function theorem, but I haven't really worked out the details. So that would be a very interesting thing to work on. I'd love to see if somebody could prove that this map is real analytic. Maybe a more interesting conjecture, though, is the following. So, Thurston showed that the Teichmüller space of a compact surface has a natural compactification by things called projective measured laminations on the surface. So this compactification is nice because the mapping class group action on the Teichmüller space extends to an action on the compactification. So you have such a compactification, and Fock and Goncharov actually constructed a similar compactification of enhanced Teichmüller space. So they have some notion of lamination on one of these punctured surfaces, and they use that to get a compactification of their enhanced Teichmüller space. And so I think a very natural conjecture is this. You could imagine that there is a compactification of the moduli space of quadratic differentials. And then you would expect that there is a continuous map from that compactification to the Thurston compactification of Teichmüller space. And it should extend the map that I defined here in this talk. So that would be very interesting if somebody could show that. And maybe finally, so for a punctured surface, Fock and Goncharov have defined what they call higher Teichmüller space, which is a higher rank version of their enhanced Teichmüller space. So this was the subject of their massive IHES paper from 2006. They constructed these enhanced Teichmüller spaces. And in view of what I have explained here today, you could conjecture that there's some higher rank generalization of this map that maps some appropriate space of differentials into the Fock-Goncharov higher Teichmüller space. And it's sort of, you can sort of see what needs to be done here. So I didn't really explain it from this point of view, but the map that I constructed is basically it's basically using the non-abelian Hodge correspondence. So non-abelian Hodge correspondence in general is relating SLN Higgs bundles to the SLN character variety of a surface. And if you have a holomorphic quadratic differential on a surface, that corresponds to a certain Higgs bundle. So there's in fact a collection of Higgs bundles. It's called the Hitchin section, which is parametrized by the space of holomorphic quadratic differentials on a surface. And that Hitchin section gets mapped precisely onto the Teichmüller space of the surface via this non-abelian Hodge correspondence. So one can say that the map that we've been talking about here is the non-abelian Hodge map restricted to the Hitchin section. In the higher rank case, the space of quadratic differentials gets replaced by a direct sum where you take quadratic differentials plus cubic differentials plus higher order differentials up to degree n, say. And then the non-abelian Hodge correspondence would map that Hitchin section to a corresponding Hitchin component in the character variety of the surface. And there are certainly many details to be worked out, but one would expect that that after defining the moduli spaces in the appropriate way, one gets a map from some moduli space of differentials to the Fock-Goncharov higher Teichmüller space. So I hope that this has been interesting to people, and that somebody will maybe be inspired to work on some of these problems. But that's all I have to say to you today. So thanks very much for your attention.
Thank you. Let me first stop the recording.